Alright, so here we are with the Chapter 5, Section 1 notes. We're going to start trig proofs, very exciting, through identities here. Basically, when we do our proofs here, it just means that we are going to basically be doing algebra and showing our work. So, so we'll kind of talk about how that goes. So the first thing that you're going to need, and of course you can be looking at your Chapter 5 formula sheet, this is kind of our first idea here, is the basic trig identities, right? Okay, so the reciprocal identities that cosecant happens to be 1 over sine, secant is 1 over cosine, etc., etc. Okay, so those are helpful because potentially someone might, a problem might give you cotangent, and you may need to rewrite as 1 over tangent, so that maybe something cancels or expands or something like that. The next piece there is quotient identities, so just understanding that tangent is actually sine over cosine, and then cotangent, of course, is the reciprocal of that. So these are things that basically we're going to use to cancel things and make things work within our problems that we have. So the other piece that will come up is the Pythagorean identity. And so as we look at the Pythagorean identity, basically it's coming from, of course, a squared plus b squared equals c squared. But as we think of the unit circle, your a and your b values are your lengths, right? Which would be cosine, for instance, and sine. And so if we take that cosine and sine and square them individually, and then add them together, it actually becomes 1 squared, which is the unit circle idea, because this is a unit length of 1. That's why we call it a unit circle. It's got a 1 involved. Okay. So that's the idea. Another piece that could happen, depending on, for instance, if you take up here all of these pieces and divide by cosine squared, oh my gosh, you get this next one. Alright, because cosine over cosine becomes 1, sine over cosine becomes tangent, and 1 over cosine is secant. Another thing that you can do, of course, rather than divide by cosine, would be dividing by sine. So if we divide everything by sine squared, you can see that we end up with the other piece. So that's this guy over here. Cotangent for cosine over sine is 1, etc. So the only thing that's kind of new with our notation of what we're doing here is this whole idea of squared. Now, the idea is that when we write cosine 2 and we don't have parentheses there, the assumed parentheses are here. And so the problem is that when you write cosine 2 squared, where is that squared applied? And so if you put parentheses here, well, it actually just means cosine of 4. But if we put the parentheses here, we actually mean cosine of 2 times cosine of 2. So in order to kind of get rid of this idea of where does the square belong, the square ends up being put right here. So, oops. Because we're not going to take the time to write cosecant of theta, another set of parentheses, squared. That's just going to take too much time, not necessary. So instead we have our little 2 up there. Alright, so that's one thing that kind of shows up. Another piece is your cofunction identities. And the idea of your cofunction identities is that sine can be cosine, you've just shifted it by a phase shift. So all of these are going to be able to be rewritten as the previous one with your phase shift of pi over 2. So if you ever, for instance, have a cosine in an identity of some sort, you can rewrite it as sine of pi over 2 minus theta as its cofunction, because maybe everything needs to be written as sine so that you can kind of put things together. So there's a bunch of tools here that we've got so far so that we can replace pieces with other things in order to make them simpler. Alright. So, our first example here is the fact that we're going to use basic trig identities to simplify. So the problem with simplify, of course, is that it doesn't always mean smaller, okay, even though they both start with S, okay, but the idea is that simplification. So sometimes that means because we're not supposed to have radicals on the bottom, that kind of thing. So in order to simplify this a little bit, we need to understand that tangent, as we've seen over here, is sine over cosine. So if tangent is equal to sine over cosine, we can rewrite this as cosine of x times tangent of x, but tangent of x is going to be written as sine of x over cosine of x. The next step of this, of course, is that cosine is technically over 1, and so to multiply a fraction, you would do the top, which is cosine of x, and sine of x times the top, and then 1 the bottom times the other bottom, cosine of x. And so because of that, oh my gosh, we get to cancel the cosines and realize that this entire identity actually just equals sine of x. And we're done. Because I doubt that we can get any more simpler than sine of x. However, what if it said use basic trig identities to write this as a cosine? Well, then you'd go back over here to this idea and you'd say, oh, well, actually, cosine of this is sine. So then you could replace what we had with cosine of pi over 2 minus theta. So it all depends on kind of what the directions are saying here. So this next one is use the basic identities to simplify the expression here. So we will go over some strategies, but one of the strategies is to kind of expand as much as possible. And so, for instance, when I see a cotangent, I always want to rewrite that as what cotangent actually equals in sines and cosines. So I usually start by writing that as cosine of theta over sine of theta. Okay. The next piece, oh, and I've changed the variable to theta somehow. Okay, so cosine over sine. Alright, now this top piece here, you might think, oh, well, let's just write that as sine and sine instead of sine squared. But actually, if you see this 1 is always kind of a key implication or idea that you're going to actually use a Pythagorean identity. So hopefully you can see that if I rearrange this piece here, okay, by subtracting the sine over to the other side, so if I subtract sine squared over to the other side, I've now made the phrase cosine squared of theta is actually equal to 1 minus sine of theta, sine squared of theta. So if 1 minus sine squared of theta actually equals cosine squared of theta, then we can rewrite this as cosine squared of x in this case. And again, that's because of that Pythagorean identity. Of course, this is when we would want to rewrite our cosine squared. So we've got cosine squared as cosine of x times cosine of x. And then we still have this fraction of cosine of x over sine of x. But of course, if you flip your fractions and multiply by your reciprocal, we can get rid of division. So I can actually rewrite this as cosine of x times cosine of x times the flip of the other fraction, so sine of x over cosine of x. From there, I can take the time to write this all as one fraction, so cosine of x times cosine of x times sine of x on top over cosine of x, and therefore, oh my gosh, cosines will not all of them cancel, of course, but one of the cosines with one of the cosines on bottom, and so the only thing left here is a cosine and a sine on top. So the simplification of having this fancy squared thing up here and a cotangent is that it actually becomes cosine of x sine of x. Alright, so if we move on, this one's saying use your basic identities to simplify the expression. Again, one major step is anytime you see cotangent or tangent or something squared, you're going to want to write it as its cosines or sines independently. So cotangent, for instance, is actually cosine over sine. And cosine of pi over 2 minus x is actually going back to our identities here, where cosine of pi over 2 minus x, or minus a variable, is actually sine. Alright, and so because of that, we can write it as one fraction, so we can write it as cosine of x, sine of x, over sine of x, times 1 technically. And then we can simplify if we need to. So for instance, this sine and this sine cancel, and so you're actually just left with cosine of x, technically over 1, but we don't need that. So again, this entire phrase at the beginning has now become this one piece, which hopefully seems more simple. Alright, let's see. The next one here. This is when we actually get into the more algebra idea of this. And so if we think of it as the fact that there's sine cubed, or I kind of think of it as x's and y's. So if I think of this as x cubed plus xy squared, hopefully you can see that I've made x as my sine and y as my cosine. And so I can actually divide out, since they both have one, an x from both of these pieces. And so out front is going to be an x with an x squared plus a y squared in there. But of course that's not actually what the equation has. I've actually divided out a sine. So sine of x is going to be multiplied by sine squared of x plus cosine squared of x. Gonna need to move this over a little bit. Alright, so what it becomes again is a sine out front, and then in parentheses a sine squared of x plus a cosine squared of x. And so hopefully anytime that you see a squared involved and a cosine, a sine and a cosine squared, hopefully that brings you back to the only thing that we mentioned today, which has a squared, which is the fact that cosine squared plus sine squared is actually 1. So going back over here, we have now decided that this, by your Pythagorean identity, actually equals 1. So that actually means that you have sine of x times 1, which of course doesn't change much, and so you have sine of x. And so these are what we're calling our proofs, okay? And so the idea, of course, is that you're doing that algebra, or you're doing those steps, you're showing how you get from one to the next, maybe even identifying the property as you're doing it, and that shows me that you understand the process of getting from this original statement to its simplified version. Alright, so the next one here, I'm just doing a bunch of examples. We've got 2 more. Let's see. We've got secant of x plus 1 and secant of x minus 1 on top being multiplied, and sine squared of x on the bottom. So, as I mentioned, it is kind of like doing your algebra, but just with some trig here. So instead of thinking of it as secant plus 1 and secant minus 1, think of it as x plus 1 and x minus 1. Because what we're actually going to be doing is going over here and expanding. So if I expand x plus 1 and x minus 1, which is what I would be doing if this was just a regular equation, would be, or an algebraic equation, I would get x squared, 1x, negative 1x, and negative 1, which would ultimately become x squared minus 1. But of course what I've done is made x equal to secant, And so when I rewrite this, I'm going to have to write it as secant squared of x minus 1, and then that is going to be all over the original sine squared that would have been there. So then we go back to the fact that this is a squared, and so one way of kind of undoing that is by writing it as secant times secant. But again, I see a squared, and I also think that maybe there's a Pythagorean identity. For instance, if I look at this piece over here, I can go ahead and subtract a 1 from both sides, and I end up with the statement that tangent squared of theta equals secant squared of theta minus 1. And so hopefully you can see that we have a secant squared minus 1, and so by that Pythagorean identity, it's going to equal equal tangent squared. And so we rewrite this numerator as tangent squared of x over sine squared of x, which of course tangent is actually going to be sine squared of x over cosine squared of x, and all of that over sine squared of x. But of course fractions, so let's go ahead and rewrite that as sine squared of x, the first fraction, multiplied by the flip of the second fraction. So this is technically over 1. And so we can do 1 over sine squared. All of that can be actually one fraction, and so if we cancel our sine squareds, we get 1 over cosine squared. And of course that's not even done yet, because 1 over cosine squared is also known as secant squared. Yikes. And so you're sitting there thinking, how am I going to get all of those pieces? Well, you only have these 3 things that you can use to rewrite things. Is it a Pythagorean identity? No, yes. Is it a cofunction? Is there some sort of pi over 2 in there? Or is it just your tangents, cotangents? And so using those 3 ideas, you're going to try to get to the end. So sometimes when you're doing this, it is easier to look at the beginning and look at the end and kind of trying to piece the way there. So it is okay to look at the answer key and say, what is it that I'm trying to get to, and see if you can piece your way like backwards to get there. Our last example here, and of course that means it's probably more intricate, is your cosine of x over 1 minus sine squared. Immediately when I see 1 minus sine squared, I know that my Pythagorean identity is going to be used. 1 minus sine squared in your Pythagorean identity would mean that I've moved the sine squared over to be with the 1, and so I actually have cosine squared of theta equal to 1 minus sine squared of theta. And you'll see that on my formula sheet, I did actually take the time to rewrite some of those identities so that you could kind of see. For instance, 1 minus sine squared is cosine squared. And so 1 minus sine squared means that I'll rewrite this entire thing so that I have cosine and cosine squared. And then I'm going to subtract sine squared, which was given, and cosine. Alright, so hopefully you can see on the left side that cosine over cosine might actually cancel a little bit. So if we reduce both of these by a cosine of x, we're going to have 1 over cosine on the bottom, minus sine squared of x and cosine of x. And so because they have a common denominator, yay fractions, we can make this all one story of 1 minus sine squared of x over cosine of x, just cosine, 1 minus sine squared, again, as we just had up here, is cosine squared. So by your Pythagorean identity, we're going to end up with cosine squared of x over cosine of x. And since that's 2 cosines on top and 1 on the bottom, if we divide by a cosine and another cosine, we're going to end up with just cosine of x. All of that for just a cosine of x. Alright, anyway, feels satisfying. Okay. So, our assignment, of course, will be given in our next lesson, so you can go ahead and check that out. But you will want to kind of have this reference sheet as you're going through, so that you can kind of say, is it one of these reciprocal identities? We've done quotient identities. Pythagorean identities was kind of introduced a lot today. Cofunction identities we've known by understanding phase shifts, but now we can actually use them algebraically. And then our next lesson is going to go on to sums and differences. So just taking a look at these top few here that you can play around with to rewrite and simplify.